Okay, good morning. So we're now well into our way into the study of rotation matrices and more generally rigid body motions. So today I'd like to sort of briefly review the Euler angles that we studied last lecture, okay, and give you maybe a little more details and discussion about Euler angles. And then I'm going to show you another three-parameter representation for our rotations. I think it's much better than Euler angles, and I hope you'll agree with me. But to get there, okay, to get to this promised land, we have to go through the desert. Okay, so that means we have to do a little bit of work, a little bit of struggle, and we're going to be doing some math today. Okay, so specifically we're going to be using results from differential equations, okay, linear differential equations. Now, most of you know the basics of linear differential equations in 1 dimensions, maybe 2 dimensions. We're going to take it up higher, okay, to n dimensions, okay, and show you. Some of you might know this, but show you how to generalize the results you learned for 1 and 2 dimensional linear differential equations to the n-dimensional case. And what that will give us is it's going to give us a very powerful tool that we can then use to come up with new parameterizations for rotations and later for rigid body motions. Okay? Okay, so let's get to work. Let's start with Euler angles. Okay, get my tools ready. Okay, so last time we looked at Euler angles. Okay, and the way I motivated this the Euler angles is through a little bit of reverse engineering. Okay, so we looked at an actual robot wrist. Okay, and we worked backwards. We said, well, how can we control the orientation? How can we determine the orientation of this wrist as a function of its joint angles? Okay, so the wrist I drew for you looked like this. Okay, Okay. Let's line that up correctly. All right. Okay, so it's maybe not the kind of wrist that you're used to seeing, okay, but the function is the same. Okay, so here's the end effector or gripper. Okay. Okay, so it has 3 joints, 1, 2, 3 rotating joints. Okay, and let's suppose that this joint here is attached to the ceiling, like so. And we rotate about this axis by an angle, say, alpha. Rotate about this axis by beta. Rotate around this axis by angle gamma. Okay? Okay, let's now suppose that the end effector frame is attached here. Okay, there's my end effector frame. And my fixed frame is attached here. Let me draw it over here. Okay, so the origin of the fixed frame is there. Okay, let me call this. So what I want to know is I want to know the orientation of this end effector frame as a function of the angles alpha, beta, and gamma. Okay? That's what I want to know. And to solve this problem, I'm going to break it up into a set of smaller problems. Okay, put the results together. And the way I'm going to do that is I'm going to attach frames to the links. So here's frame 1 attached to link 1. Here's frame 2 attached to link number 2. And my end effector frame, I'm going to call frame 3. Okay? And let's call the ground frame 0. Okay? Okay, so what I showed you last time was that the orientation of this frame number 3, okay, written as a rotation matrix, okay, looks like the following. Okay, it's a multiplication of 3 rotation matrices. Okay, rotation around the z-axis by alpha, followed by rotation around the y-axis by beta, followed by rotation around the x-axis by gamma. Okay, so you remember the exact form of these matrices. I'm not going to write it down again. Okay, so where did this come from? Well, this came from the observation that our R is in fact R03. Okay, and this is just R01. Okay, so frame 1 as seen from frame 0. So imagine yourself standing at frame 0, looking at frame 1, okay, and writing down its orientation as a rotation matrix. That's R01. Okay, so you'll see that this only depends on alpha. Okay, now imagine you're standing at frame 1, observing frame 2, write down the orientation, okay, as a rotation matrix. It only depends on beta. And finally, same thing. You're standing at frame 2, observing frame 3. Okay, so that's what it looks like. So we make these identifications. Okay, and so this is how we get the rotation R as a function of alpha, beta, and gamma. Okay, so the alpha, beta, and gamma defined this way are the what? Are the ZYX Euler angles, okay? ZYX. Okay. Okay, so we know how to go from alpha, beta, gamma to the orientation, R. Okay. To go the other way, okay. So given R, some rotation matrix, suppose we want to find alpha, beta, gamma. Okay, so this is the inverse problem. And so we looked at this too. Okay, we did it the old-fashioned way, right? We wrote down we multiplied these 3 matrices. Okay, stared at the expressions for a while, and then used trigonometry. Okay, so the old-fashioned brute force hard work method. And we found that we can get alpha, beta, gamma by following this formula, this procedure. So beta is the inverse tangent of minus R31 over plus minus R11 square plus R21 square. Okay. Now you see this plus minus here. Okay, so that indicates there are 2 possible solutions. Okay. Now in an actual implementation, okay, so if you're out in the workforce and you're actually a practicing engineer writing software to implement this, way you would do it, okay, is you would use something called the A tan2 function. Okay, so you would say beta is A tan2, okay, y minus R31 over, okay, you have two choices, plus or minus. Let's just take plus for now. Okay, so those of you who've done a little bit of programming, numerical programming, okay, you know what this is, right? So A tan2 y over yx. This is the arctangent, okay? It's this, but it takes into account the signs of y and x, okay? Into account. Okay, so for example, if in the xy plane, here's x, here's y. Suppose x and y are equal to 1 and 1. Okay. Okay. Now if we take the A tan2 function of this point, that gives us an angle, right? Pi over 4. Okay. But now if we take A tan2 of, say, minus 1, minus 1, okay. Okay. Then the angle associated with this is, okay, so it's 3 pi over 4. Okay, so A tan2, you know, is preferred for implementation because it takes into account the sign of these arguments. Okay, all right. So unfortunately, I have to erase this masterpiece. Okay, and then find beta first, then find alpha and gamma according to these formulas. So alpha is just A tan2 of R21 over R11, and gamma is A tan2 of R32 over R33. Okay. All right, and let's see. We also have to, okay, so we had a choice here. We could have taken plus or minus. We deliberately chose plus. Okay, so if we take the positive version of this and apply A tan2, then you can see that the range of beta, okay, this is always positive. Okay, it's always positive. Okay, so the range of beta is between 0 and, or sorry, not 0, minus pi and pi. Okay, right, because the x argument is always positive. Question? Yes. Okay. Sorry about that. Okay, so, okay, let's get back to here. So beta is between minus pi and pi, or sorry, minus pi over 2, pi over 2. Okay, and alpha and gamma are both between 0 and 2 pi. Okay. All right. Okay, so this works, right? We checked the steps. Okay, now there is one more thing to be careful of. Okay, so we first find beta. If beta happens to be 90 degrees or minus 90 degrees, okay, then we have to remember that there are going to be multiple solutions. Okay, in fact, there's going to be an infinite number of solutions. Okay. So when we find alpha and gamma, okay, we can't find alpha and gamma uniquely. Okay, there is a one-parameter family of solutions. And one parameter okay, so we kind of saw why. All right. Now I drew that wrist for you. Let me try to draw that wrist again. This time for the case where beta equals 90 degrees. Okay, so let's try it again. Okay, this is where this is where I really regret not having learned how to do basic drawing. Okay, try it again here. All right, so it looks something like that. Okay, so I don't know, I think there's a problem with the top part of the drawing here. That's why the bottom looks kind of weird, but anyways. All right, so anyway, suppose, okay, so I rotate beta 90 degrees. Okay, the wrist looks like this. Okay. Suppose I say this is the 0 configuration or the home configuration of the wrist. Okay. In other words, I'm going to define alpha, beta, and gamma such that if alpha, beta, gamma are all 0, the wrist looks like this, is in this configuration. Okay? So suppose I define the 0 or the home configuration of wrist as shown. Okay, I can do that, right? So I'm going to say, well, I think this is a more natural home position. So you do that. You can do the same game again. Okay, so you draw the 0 frame up here. Okay, draw link frames here, link 2 frame here, and then end effector will be here, link 3 frame here. Okay, and then angles are defined in this way. This is alpha, this is beta, this is actually let's do it. Okay, let's just define it this way. Gamma. Okay, so I do the same thing, okay, but with this as the home position. In that case, so R03 is equal to rotation about the z-axis by alpha, followed by rotation about the y-axis by beta, followed by, this time, rotation about the not the x-axis, but the z-axis, by gamma. Okay, so this is R01, this is R12, this is R23. Okay, and this is my R. Okay, so it's the same wrist, same wrist. All I've done is just redefine the home configuration. Okay, then I attach reference frames, do the same analysis. I get this. Okay, so the alpha, beta, gamma defined this way, okay, also is a valid three parameter representation for rotations. Okay, but it's different here. So alpha, beta, gamma defined this way. Defined as above. Okay, these are called the ZYZ Euler angles. All right. Okay, so you see there are many different type possibilities for defining Euler angles, right? I could have defined the home configuration this way. I could have defined the home configuration maybe in another configuration, right? Maybe rotate beta not 90 degrees, but 180 degrees. Okay? Or I can rotate alpha 90 degrees and then set, right, beta and gamma to some arbitrary angles and call that the home position. Okay? So you see that Euler angles, so if you just say Euler angles, that's not very helpful. Okay? You have to specify what Euler angles. ZYX, ZYZ, XYZ, YZX, whatever. Okay? And you see that, so you get the idea that I can be much more general with this. In fact, how general can I be? Okay? Well, you see that the key thing to making this work is that I just need to make sure I define these axes here such that they are orthogonal to each other. Okay, so axis 1 times axis 2. Let's go to the next line. Times okay. Any parameterization of this form where axis 1 and axis 2 are orthogonal, okay, and axis 2 and axis 3 are orthogonal. Sorry, this is axis 2. Okay, this works. Okay, this works. Okay, it works, meaning it's a valid 3-parameter representation for rotations. Okay. So note that this does not mean that axis 1 and axis 3 have to be orthogonal. Okay. In fact, they can be the same, just like here. Okay. So this works. Okay. So that's the most general way to use Euler angles. Okay. And however you define the axes, okay, you'll find that alpha and beta, the range is 2 pi, or sorry, alpha and gamma, the range is 2 pi, and beta range is typically pi. Okay, And when beta is at the limits, okay, you'll have this. Okay, there'll be a one parameter family of solutions. Okay. All right, so there you go. So when you're using Euler angles, okay, to describe orientations, always specify which Euler angles. Okay, is it ZYX, ZYZ, XYZ? Okay, whatever permutation you use. Okay. All right, so there you go, Euler angles. Let me change my perspective a little bit. Okay. Okay, two hands went up at the same time. I think you were about 5 milliseconds faster, so yeah.
베타 범위가 파이만 되는 이유를 모르겠어요. 그러니까
베타 범위가 파이만 되는 이유. So the question was, why is the range for beta pi rather than 2 pi? And the answer is that it can be 2 pi, but then you have double solutions. Okay, so this is if you want to cover SO3 once. Okay, so let me mention that. Okay, to cover the rotation group once. Okay, so what's happening here is that if you allow beta to be the range 2 pi, okay, so a familiar example is, okay, so okay, so here's the globe, right? Latitude and longitude. Okay, so we usually say this goes from 0 to 2 pi. Okay, and this angle, okay, is from 0 to pi. Okay, now we can go 0 to 2 pi, but then it covers the Earth twice. Okay, so this is what's going on here. That's why we have beta range pi. We can make it go from 0 to 2 pi, okay, or range be 2 pi, but then you have two solutions for every rotation. Okay, so if you just want one solution, okay, you want to cut the range of beta to be just pi. Okay, okay, there was another question in the back. Maybe it was the same question. Okay, good. All right, okay, so let's go back to the change of perspective. Here's what I'm going to do. Here's my fixed frame, x, y, z. Okay, I have a vector. Let me call it v. Try to draw this. Okay, so here's my vector v. Okay. I'm now going to rotate this vector v around the x-axis. Okay, rotate around the x-axis. So it's going to rotate maybe something like that. So it goes to here. Okay, and let's rotate. Let's say this angle is gamma. Okay, so my v here is now rotated around the x-axis by angle gamma to the vector v prime. Okay. Okay, now it's v prime. Let's see. Well, let's see. Since we're rotating around the x-axis, looks like the x component of v and the x component of v prime should be the same. Okay, should be the same. But the y and z components are now different, right? Okay, so v prime. What does it look like? Well, let me write it down for you. Okay, so now we're writing everything here in terms of the fixed frame coordinates x, y, z. Okay, so that's v prime. Okay, now I can stand here and explain this to you for 5 minutes. Best way to convince yourself is to go home, draw pictures, okay, and you'll be convinced in less than 5 minutes, I guarantee it. Okay, so right now, trust me, take my word for it. Okay, this is what v prime looks like. Okay, okay, this is kind of fun. So this time I'm going to rotate v prime around the y-axis. Okay, so let me try to draw it again here. Okay, same fixed frame. Okay, but now I have v prime here. Now I'm going to rotate it around the y-axis by some angle. Let me call it beta. Okay, so, wow, this is a beta. Okay, so v double prime, let me call the result v double prime. And this is v prime here. So v double prime is v prime rotated around the axis y hat by angle beta. Okay? Okay, so here you have to, again, trust me, take my word for it, and convince yourself either now or maybe a little bit later. V double prime is going to be sine beta 0 times v prime. Okay. All right. Now, finally, you can guess what I'm going to be doing next. Okay, I'm going to rotate v double prime around the z-axis by angle alpha. Okay, so here we go. So here's v double prime. Okay, so rotate around the z-axis by angle alpha. Okay, call my result v triple prime. Okay, and then I can write down v triple prime. Okay, so v triple prime. Okay, is a rotation around the z-axis. Okay, so it's v2 prime rotated around z-axis, okay, by alpha. Okay, and this equals cosine alpha, sine alpha 0 minus sine alpha, cosine alpha 0, 0, 0, 1 times v double prime. Okay, so if I now have some vector v, and I do 3 rotations, okay? Rotate around the fixed frame x-axis by gamma. Next, rotate by the fixed frame y-axis by beta, okay? Finally, rotate around the fixed frame z-axis by alpha, okay? All the rotations were done with respect to the fixed frame, okay? fixed frame axes. Then I get my result, v triple prime, okay? So v triple prime is what? Simply rotation. Let's now use our new notation. So it's rotation around the z-axis by alpha, rotation around y-axis by beta, rotation around x-axis by alpha times v. Okay? So here's my first rotation. Gives me v prime. This is v2 prime. Total, the whole thing is v3 prime. Okay? All right. So now, suppose I take my original v to be x-axis. Okay? Or take it to be my y-axis. Or maybe the z-axis. Okay? So if I have some frame, okay, and I rotate this frame around the fixed frame x-axis by some angle gamma, then around the fixed frame y-axis by some angle beta, and finally around the fixed frame, sorry, that was y-axis, finally around the fixed frame z-axis by some alpha, I get a rotation. Okay? So if r, the initial r is 1, 0, 0, 0, 1, 0, 0, 0, 1, okay, then r3 prime is just this. Okay, so z alpha rotation y beta rotation x gamma. Okay. All right, now if you look at this formula, this is exactly the same as the ZYX Euler angles. Okay? But remember the interpretation of the ZYX Euler angles, okay? So in the ZYX Euler angles, we start with a frame, x, y, z, okay? First, rotate around the z-axis by alpha, okay? Next, rotate around the new y-axis by beta, and then rotate around this new x-axis by gamma, okay? I get my rotation. Okay? Now, start with the same frame. This time I rotate around the fixed frame x-axis, which is the same, by gamma. Okay? Next, I rotate around the fixed frame y-axis. Okay, that's here, by beta. Next, I rotate around the fixed frame z-axis, okay, by alpha. I get the same rotation. I get the same orientation. Okay, so the formula is the same. Okay, but now we have two different ways of getting there. Okay, in the ZYX Euler angle representation, we're rotating z, then y, then x. Okay, and these rotations are with respect to the moving frame. Okay, in this interpretation, we're rotating x, y, z. Okay, but the rotations are with respect to the fixed frame. Okay, so we have two formulas, the same formula, two different ways to get there physically. Okay, all right, so this interpretation of the same formula, people use different names for it. We call it the, I don't know, the fixed axis. Okay, so this version is the x, y, z. And again, there doesn't seem to be standard terminology for this, so we'll just call it the XYZ fixed axis representation. And the thing to note is the formulas are the same. Okay? Same formula as the ZYX Euler angle formula. Okay? Okay, so it's pretty important to understand that there are two physically different ways of getting to the same orientation. Okay? The order of rotations is reversed. Okay? And the rotations are taken in one case with respect to the moving frame, in one case with respect to the fixed frame. Okay? Okay, so I think that's a good thing to know. All right.